Soldiers can die if you can't maneuver and you end up stuck somewhere.
We had 2 occasions where the vehicles turned over and soldiers died because they drowned. They flipped over because of the mobility.
Since Hannibal crossed the Alps with elephants, mobility is always a challenge for vehicles, whether it's getting stuck in 1917 in the fields in France or Afghanistan. When vehicles become immobilized, troops are put at risk and the mission is jeopardized.
Being able to predict mobility is going to just increase the survivability of our soldiers and our vehicles. Anything that we can do to protect our soldiers, we should be doing, and mobility is a key factor in survivability.
It's a subject that NATO has been exploring for years, how to predict mobility.
NATO expands in Europe from the north, from Norway, to the south to Romania. We have the whole range of terrain we can imagine in Europe, and then we have North America and stabilization operations in very desert areas like Iraq or Afghanistan. So when we can then predict what vehicle we need or in which terrain our troops have to fight, gives us a big advantage over our enemy.
Out on the battlefield, commanders have to consider many factors when deciding which vehicles to deploy.
So you got to understand the capabilities of the vehicle. You got to understand the terrain that you're operating in. HEMTs or logistical vehicles are really good on secondary roads, but it's really difficult for them to go across big rocky terrain. And then for the U.S. Army, we have Abrams and Bradley. There are combat track vehicles, and they're just significantly more mobile when you get into rocky, difficult, wet, soft soil terrain.
The current industry standard tool for predicting mobility is the NATO Reference Mobility Model, a software tool that has detailed soil data for different regions of the world and predicts terrain traversability. But it dates back to the 70s. A NATO task group is now developing a new version of the model, referred to as the NextGeneration NATO Reference Mobility Model.
The current model is outdated, it's old. It's still useful, but the current systems are different nowadays. Our vehicles have stability control systems, they have tire pressure systems, and all those types of systems make a difference in your mobility off-road. And so we really need to update the NATO standards to be able to predict those types of things. And also, computer simulations have come a long way since the 70s, so we can do a lot on a computer nowadays that we couldn't before. So we're talking about complex terra mechanics and simple terra mechanics, and in complex terra mechanics, we're really trying to model the physics of the soil and the interaction of the vehicle with the soil. And so there's a lot that can be done if we understand the variability in the soil and the terrain with predicting mobility.
We developed this tool in a NATO task group, and this task group is in the Science and Technology Organization of the NATO. So there are experts from industry, government and so on. They all work together, bring in their expertise and develop this common tool for them. And then they agree also on a standard.
There's many different factors that can affect mobility. You have the terrain itself, which is the type of terrain, the type of soil, the constituents within the soil, the water content within the soil. It all has an impact on mobility. And then you have the vehicle level characteristics and how the vehicle is designed, the types of suspension, the type, whether it's road wheels, the size of the wheel, the amount of power you're delivering to the wheel, the tractive effort we call it, or the track systems. So it's not only the design of the vehicle that you need to take into account, but you also have to be able to accurately characterize the soil and understand the strength of the soil, how well it can carry weight, and then how long it will withstand repeated trafficability. So the first vehicle may go over very easily, but then the second, third, fourth, it gets more and more difficult as the soil breaks down.
Soil varies a lot. So there's all different sorts of soils and all different mixes of those sorts of things. So sand, silt, clay, organic material, gravels, rocks, whatever. And if we look at the NATO countries, those soils vary up from all the way from a dry sand on a beach somewhere in France up into high organic materials and clays in places like Estonia and Poland and the northern Baltics. The project that we're working on has to cover all of those, and we have to be able to model that and know what's going to happen to the vehicle when it dries in. One of the things that we developed for this project is a piece of equipment called a bevimeter. And the bevimeter is a relatively large piece of equipment that's designed to measure two different things. And one of those is what we call shear. And what that does is it gives us an idea of what traction we can get out of the tires. So how is that tire going to grab on the soil, and what strength can we get out of it as it spins? The other side of it is a thing that we call plate sinkage. And the plate sinkage gives us a compressive strength or bearing strength. And what that does is it tells us how much is the vehicle going to sink. So coupled, we get vehicle sink so much, and as it's moving along, as it's sinking, how much can it grab the soil and pull itself along? And that's pretty much the basis of mobility, those two things coupled together. So the bevimeter is a device to be able to go out in the field and get those measurements, then be able to put them into the models and spit back out the mobility.
Much of the vehicle data for the mobility modelling is gathered at the Kiwi Nor Research Centre in Michigan, a 900-acre multi-terrain site specifically designed for ground vehicle research.
Certain areas of the test course have been constructed to represent certain interesting types of terrain, especially types of terrain that we might not particularly have. Desert terrain, rocky terrain, and such. The whole point of doing the testing is to collect the real-world data and bring that back into the design area, back into where we can manipulate the vehicle designs and look at different changes and things that might affect or improve ground vehicle mobility. To do that, we have to collect the data, and the vehicles are heavily instrumented. Accelerometers, wheel force sensors, GPS trackers. That data is created into a large database, and then that is then digested and reduced into usable, comprehensible data set that the vehicle designer can use to further the vehicle design.
While previous mobility models have combined data from vehicle terrain and soil testing, for the NextGeneration NATO reference mobility model, software companies are getting involved for the first time. A number of vendors have been called upon to use the data to produce models which simulate terrain traversability.
So what we're trying to do is generate a common framework that people in the mobility industry can use for predicting soft soil mobility in particular. So we are leveraging new simulation technologies that are already mature on hard surface, so regular ground vehicle that you use every day, and taking that off-road. So the importance here is to be able to predict when a vehicle that might not even have been designed yet, that's in the design process, trying to say the capabilities of this vehicle on the type of terrains and soils that it will experience. You don't want to have a vehicle that you don't know what its mobility performance is. So we're trying to do this in an accurate way using the latest simulation technologies.
The vehicle data itself was mostly in a spreadsheet with a bunch of tables. There were probably 20 tables of data for transmission data, wheel data, suspension data. The terrain data is probably the biggest source. This is probably about 2 gigabytes of data just for the triangles and the surface that we're driving over. On top of that, there's all the soil definitions, where all the soil testing that's done to measure the stiffness of the soil and the shear strength of the soil. That's all other information that has to go into it as well. If we need to figure out how things are laid out and how they're positioned, this is a 3D environment that lets us see everything and place it in the right place in the universe. It's also the simulation environment. Once we're playing it, we can actually see what's happening now that the simulation is running. So this software actually covers all the different aspects of the simulation, from once you have the initial data, you've entered it into the model, you've collected all the different pieces together, and finally you can actually run the data. And on top of that, we can also see plots of what's happening inside the vehicle itself. So I can see live speeds, I can see live suspension performance, I can see live soil traction, tire slip, vehicle RPM. All of these values can also be read live as I'm working on this.
Making a model allows us to do a lot more virtual comparison based on a lot of different environmental aspects. So whether or not it's in a given pavement situation or off-road situation, if you have a virtual model, you can do an endless amount of what-if studies. And it can be not only on the physical environment that the vehicle is operating in, but it could be the vehicle itself. So if you wanted to understand how the vehicle performed with different tires, for example, you could easily swap out the tires and run them around and get an understanding of its performance without having to do any physical testing.
Each NATO nation has its own methods of predicting mobility. The aim with the NextGeneration NATO reference mobility model is to harmonise their approach and provide a set of standards in a way that could reduce procurement risks, enabling alternative solutions to be considered.
So that's why this NATO reference mobility model is so important. Is from an acquisition perspective, when we buy systems, we need to understand how good they are from a mobility perspective. But also then operationally, we need to be able to understand how well can I go from point A to point B? Can I carry out this operation with this vehicle or a set of vehicles? So another nice thing about the NATO reference mobility model is that it can be run very quickly. So you can run it over a large swath of land and look at all these different types of vehicles and how fast they might go through some area. So that's important from an operational planning perspective. It's important from an acquisition perspective of deciding which vehicles to use or buy. If, for example, two companies come to us and say, you know, we have two different vehicles and we want to evaluate which vehicle is better, we can use the NATO reference mobility model, and that's how we often do it. We use it and we run it through scenarios and say which vehicle is actually more mobile.
If all the NATO nations would be using this as a standard, to design to these standards, they test to these standards, so that it can be operational anywhere in the NATO countries. It's completely interoperable. So that is in itself is very important that is done at the NATO level.
Ultimately, this is the first step. We're hoping to develop a standard modeling approach that will allow NATO nations to use various levels of multi-body physics models at the procurement stage of a vehicle, at the notional design stage of vehicles, and operationally in the field for the operational user at the end.
The challenge for the NATO task group is keeping up with advancements in technology. While most of their attention has been spent on manned ground vehicles, increasingly on the battlefield, commanders are using unmanned systems.
When we get into autonomy and autonomous vehicles, we don't have a good way to make that assessment. The NATO reference mobility model cannot do that. So we're proposing to form a new exploratory team under NATO to start looking at, beyond the next generation of NATO reference mobility models, how do you predict autonomous system and their mobility? So obviously that's an important area for quite a few of our partner nations.
So if I can picture myself as a commander or a platoon leader trying to plan a mission within a certain time period, and I have a limited amount of time to do that. So if I can understand, other than just looking at a map, what that terrain looks like on the ground, and somebody can tell me for sure that I can maneuver these elements through that area within a certain time period, that's the most important piece to me.
At the end of the day, it's all about supporting the warfighter, making them more effective, keeping them safe, and letting them come home alive and in good health after we ask them to do our nation's work.